In this video, we're going to see how to sketch higher degree polynomials above a cubic. So we're talking about power 4, power 5, and beyond. We're going to look at how to sketch those. Then, after we've done that, we'll have a look at how to solve some applications of polynomials. So we're talking about finding maximums or minimums and the families of functions style questions. Enjoy! Okay, let's get right into it. So what we're going to look at today is how to handle higher degree polynomials, higher than, for instance, cubics. So pretty much we're just going to be looking at how to handle powers of 4 polynomials and above. If you're looking for places to specifically revise this, these are the chapters and these are the books that you might want to specifically hone in on if you're looking for this kind of content. But okay, first things first, odd and even polynomials. What's that all about? Well, what I'm talking about here is when you have you can almost call it like a completed square form of the polynomial. I call it the transformation or the transformed form of the polynomial, and it's because you can quite clearly see what the transformation factors are in this form. You've got a horizontal translation, you've got a vertical translation, you've got your dilation. So this form applies to all polynomials. It just means a slightly different thing depending on if you're an odd polynomial or an even polynomial. And for the context of this discussion, odd polynomials are going to be those that have powers which are odd. So whenever your n is 3, 5, 7, 9, all these odd numbers, that will be considered an odd polynomial. And the way that works is fundamentally, all odd polynomials of that form are going to effectively look like steeper and steeper cubics. So x cubed, you can see, is like the widest of the lot. It's the furthest spread out, it's the green one. And then x to the power of 7 is the tallest. It shoots up higher than all the others do because, well, when you raise something to the 7th power, it is going to be a lot bigger y value than if you had just raised it to the 3rd power. Now, that's odd polynomials of this form. More specifically, we have this idea of an odd function, which is a bit different. It has a very specific definition, and that is that f of negative x is always equal to negative f of x. So what that means in this context is, for example, if I said I had f of x, so let's pretend x equals 1, that would be this spot here on the graph. This identity means that if I were to find the equivalent negative x spot, so over here, the y value at that spot would be the negative of the y value of the previous spot. So this would be y equals 1 over here. This would be y equals negative 1 over here. Now, we'll have a look at what that might look like in an actual handwritten example. So if we had y equals x cubed, or I guess we could say f of x equals x cubed, then fundamentally if you want to prove f of negative x equals negative f of x, then one thing you might start with at the very least would be to plug in a point. So if I were to do f of negative 1, for example, that would be negative 1 cubed, which would be negative 1. So we know f of negative 1 is negative 1. Now, to prove the identity, the equation, whatever you want to call it, we would then want to test negative f of x, or in this case, because we've chosen x is 1. Remember, this was f of negative x, so the 1 became negative. F of x is going to be x equals 1 here. So negative f of 1 just means putting a negative out the front of the function and then subbing in x equals 1. So it's a minor difference, but under those circumstances, we're seeing that negative f of 1 is in fact also equal to negative 1. These two things are the same, and so at least for a single point, we've proven this identity. How to prove it for all x just means subbing in, literally, just x and negative x into those equations. And so all we're going to be doing is saying, well, okay, what would f of negative x even look like? Well, it would mean replacing every x with a negative x. And one thing you can do with odd powers is factor this negative out the front. So f of negative x is equal to negative x cubed. Now, this should be equal to negative f of x. What is negative f of x? Well, we take f of x, whatever it was, and then just put a negative sign out the front. These two things are the same, hence this function is odd. So that's pretty much all that's going on there. You sub in the negative x, and you compare that to the negative of f of x. Okay, so I've got an example here. Prove that this entire function is odd. Might be a bit hard to immediately tell that, so one thing you might do is do exactly that. You plug in the negative x, and you compare that to if it was just the negative of f of x. So f of negative x means replacing all of these x's with negative x's, and then factoring that out the front. That gives you result 1 here. From there, we're just going to test negative f of x, which means taking the whole of f of x and then putting a negative sign out the front of that, and then distributing it all the way through. You compare the two things together, they are the same, therefore the function is odd. Even polynomials. So as far as proving even, it's a little bit different function, but the idea is more or less the same. But when it comes to even polynomials specifically, these are polynomials, again, with that form ax take h. So let's find it again. Polynomials of this form specifically, where the n is even instead. And so when the n is even instead, you basically end up with steeper and steeper quadratic or parabola type equations. Okay, so from there, the power of 6 is going to be steeper. You can see it's a greater y value. If you're going to look vertically, it's a greater y value than, for example, the x squared. Again, this is because you're raising something to the power of 6 instead of just to the power of 2. Okay, so that's what they look like. Just steeper and steeper parabolas. As for proving, well, we're going to have a slightly different equation. This is f of x is always equal to f of negative x. This is usually a bit easier to prove because, well, f of x is just f of x. You don't have to do anything to that. And then negative f of x just means replacing every x. Oh, sorry, f of negative x just means replacing every x with a negative x. And inside of even powers, all the negatives will disappear. You know, if you have negative 2 squared, that's the same as saying negative 2 times negative 2. The two negatives will cancel out. Same thing works for all x. If you compare f of negative x to f of x, they are the same thing. This must be even. Okay, this leads us to a discussion about factorized polynomials. So why do we care about even power and odd power polynomials? Well, it allows you to, well, for one, sketch those types of equations, but for two, it also allows you to handle factorized forms. So one thing worth highlighting here is we've already discussed, at least in previous lectures before this point, how you might handle linear terms and repeated linear terms. So linear terms being like ax plus b. I'll even write some out actually. So if you had like a linear ax plus b, then the solution to that term specifically would be an axis intercept, an x-axis intercept. It would cut through the graph at a certain point. Whereas if you had a repeated linear term where it was squared, that would be a turning point, whatever the solution to that was. The thing I'm going to touch on now is what happens if you have a triple repeated linear term, or, you know, just a cubed linear term. This is an inflection point, and that probably wouldn't come as much surprise to you because, well, quadratics are turning points and cubics are inflection points. So really it's just knowing the difference between your quadratics and cubics. Why does this matter? Well, for one, it allows you to be able to sketch these types of graphs. The other is that it ties into the previous conversation we had about odd power and even power terms. The same thing applies here. So if you have any even power, so it's saying 2, 4, 6, all those even numbers, the solution to that term will always be a turning point. The same can be said, or at least similar can be said, for odd powers. When you have your odd powers of 3, 5, 7, 9, these are always going to be inflection points. So let's see what that's all about. We have our example here. If we want to sketch this graph, we need to know x-intercepts, y-intercepts, and the overall shape. So x-intercepts, always nice and easy using null factor law. That just means grabbing each of these terms and equaling them to 0. So we know the x-intercepts pretty easily. Only thing that'll be a little bit different is whether or not they cut, turn, or inflect, which will depend on the powers, but we'll talk about that in a bit. Y-intercept, always subbing in x equals 0. Nice and simple. Subbing in x equals 0. It's a big number, but simple concept. Okay, overall shape. What's going on here? Well, if you recall from sketching cubics, what you needed to understand for factorized cubics was where does it start and where does it end. Usually, cubics will typically start bottom left and end top right, and if they're negative, they'll start top left and end bottom right. We can take this to the next level. So what we can actually say is any odd polynomial, so any odd polynomial of that form, will start at the bottom left and end at the top right if it is positive, and it will flip that order if it's negative. So starting top left, ending bottom right. That'll be for any odd polynomial. We don't have an odd polynomial though. We have an even. Whoops, almost gave it away there. We have an even, and the reason why is because if you were to expand this all the way out, you've got an x here, 5x's here, 4x's here, that's 10x's total. So we have x to the power of 10, that is in fact an even polynomial. And so what does that matter? Well, that's going to tell us where we start and end. Even polynomials are parabola type shapes. So they start and end at the top. So top left and top right. Unless they are negative at the front, in which case you're starting and ending at the bottom left and right. In this case, we have positive x's all throughout, and so we do have a positive even polynomial. And so because of that, we know we start at top left and end at top right, which is what we see here and here. From here, we know that this term is an odd power term. Hence, this solution, which came from that term, must be an inflection point. And so if we look at that, x equals -1 is in fact an inflection point. If we zoom in all the way on that, you can see it goes, whoop, not too far in so you don't see all the pixels. X equals -1 is in fact an inflection point. You can see it wobbles at that spot. While we're at it, y-intercept, we saw that earlier, it has to cut through -625. The other term to talk about is the x minus 5 all to the power of 4. Because that is an even term, that is going to be a turning point at x equals 5. And sure enough, that's what we see over here. Turning point at x equals 5. Now, again, if you've done cubics before, which I hope you have, if you haven't, then you are definitely jumping in the deep end on this. If you remember from cubics, what we know is that turning points, or I guess even stationary points in general, that are not on the x-axis cannot be found unless you've studied calculus already. So these things up here, at this stage of your journey, if you're in year 11, you probably haven't had a look at calculus, and so finding these turning points, you just sort of got to eyeball it. Like, you know you start top left, you know you inflect at -1, you know you got to cross over at -625. The only way you can then cut at x equals 1, I guess I forgot to mention that one, we cut at x equals 1 because of this term. It's just a linear, and so it cuts. The only way you can cut through that is if you turn, and so you just draw the turning point, even if you don't know exactly where it is. Same thing over here, right? The only way you can turn at x equals 5 is if you eventually turn around and hit there again. It's worth highlighting, this will not necessarily be the midpoint. This will not necessarily be the midpoint, so don't pretend that it is. Like here, even if you were to do it between, well, where would even be the, yeah, let's not even bother. Basically, don't try to guess that it's the middle, because it may or may not be. Just sort of put it wherever feels right. If you have learned calculus, then you would well, you would suffer in this case because you have to do derivative of this and set it equal to 0. So this isn't something you'd ever have to do tech-free. Tech-active, however, for those who have done calculus, find the derivative of this using the CAS, set it equal to 0, and then that will find you all your stationary points, whatever the solution to that is, which will give you this inflection point, this turning point, this turning point, and this turning point. Lots of stationary points. Okay, and that's it for that then. If you're already in the community, there is a summary on the handwritten notes. Oh, sorry, not the handwritten notes, the printed PDF notes. Okay, that's sketching higher degree polynomials. As for the next bit, we're going to look at applications of polynomials. How do we use them in quote-unquote real-world scenarios? Again, if you're looking to figure out where to study this content, the chapter list is here. Okay, families of functions, in this case specifically families of cubics. What's going on here? Well, these are the kinds of questions where you have a series of unknown coefficients in your function, and you have to use information to figure out those unknowns. So in the context of quadratics, it's very similar to how we handle it with cubics, where there are effectively 3 main forms of cubic you might consider using, and that will be dependent on which information you have. So you might use the polynomial form, in which case you are mad because you like doing many simultaneous equations. You might use the axes intercept form, or the x-intercept form, I should say, and that will be most applicable if the information you're given are the x-intercepts. And then finally the inflection point form if you're given the inflection point. Let's find out. So, example 1. What happens if you have the inflection point and another point? Well, that inflection point there immediately tells you the b and c values. At least I've said b and c. You could use your h and k's if you like. So immediately that tells me I'm going 3 right, 1 down, and so that's going to be described by x minus 3 and then a minus 1 at the end. So already a single point is going to knock out 2 variables for us. From there, for all polynomials, there will always be this a term out the front, and you will always be solving that by subbing in another known point. I say always, let's say 95% of the time. I'm sure there's going to be some question out there that tries to throw you through a loop. This is the strategy that works or is used in the vast majority of cases. But okay, sub that point in. So x equals 4, x equals 1, y equals 1. So x equals 4 there, y equals 1 there, rearrange, solve. Sometimes you just need to know your a, b, c, and then you just give those answers. Sometimes you're told to give the new rule or the curve, and so you would write that instead. So, in summary, if you are told the inflection point, use the inflection point form. You won't be told it, you'll just be shown it, and you'll have to infer that you should use the inflection point form. What if you have axes or x-axis intercepts? Well, you use the x-axis intercept form. We have cuts at 1, 2, and 3, and so that means our linear terms should be x minus 1, x minus 2, x minus 3. Again, you got this a term, and you have this known point. Sub in your known point, solve for a, and then plug that back into the equation. Okay, and now we're going into a few more examples. I have an example for, I think, every possible scenario for cubics. One is, what if you have axis intercept and a turning point? Well, again, we know turning points on the x-axis are those repeated linear terms, and so you would use that instead. So if the turning point was at x equals negative 2, then the repeated linear should be x plus 2. Axis intercept at x equals 1 means a linear term of x minus 1. A term, point, sub in point, get your a term. This point, of course, being the y-intercept, so x equals 0, y equals negative 12. Solve for a, plug into your equation. Worst case scenario, 4 random points. This will be a CAS question. They barely do this for SACs on the when it was quadratics, when you had to do 3. They're not going to do this to you in a tech-free for for a cubic rather. How you would do it? Well, you would start with your polynomial form, and you would just go into your solve system of equations. So you've got 4 points, that gives you your 4 equations. One thing I would specifically do is make sure you define f of x before you plug it into things. So you define f of x as this polynomial, ax cubed plus bx squared, and so on. And only then do you say like f of negative 2 equals 7, because you have the point negative 2, 7. F of negative 1 equals 8, because you have that point, and so on and so forth. Saves you from typing this out 4 times. So the shortcut to get there is, well, not really a shortcut, but it's that path there, menu algebra, solve system equations. So I'll even just do it live with the TI Inspire right here. So we have menu 3 for algebra, solve system of equations, which is 7, and then again solve system of equations, which is 1. Set your equations to 4, call them A, B, C, D, hit enter, and you get the field that I just showed you. And yeah, once you solve it, you'll get that set of answers for A, B, C, D, and so you just sub that back into your polynomial. If you're instead using the Casio, it'll be found under the Math 1 menu. Just hit that button 4 times to get the 3 equations. So to demonstrate that, I'm going to go off screen ever so slightly and bring out my Casio. Okay, so Math 1 menu, so get the keyboard out, Math 1, and get the stylus out. And you can see this button here. So assuming you've defined your function already, you would hit this once, twice, and then, oh, I said hit it 4 times. Oh, I said it backwards. It should be 3 times to get 4 equations. Bugger. Alright, I'll fix that. Yeah, so you get that sort of set up there, and fundamentally it's the same idea, where this is where you put your equations, and then you're just going to do A, B, C, D. So go to your ABCs, A, comma, B, comma, C, comma, D. And then, yeah, that would be pretty much all you do there. Okay, the other main type of question is the so-called maximum/minimum problem, which is where you're told the function that describes a particular quantity, and you have to find the absolute maximum or absolute minimum value of that quantity. And the vast majority of the time, this will be a CAS question, or at least until you learn calculus. The reason why is because the vast majority of the time, you are finding a turning point. So I've got a sequence of steps that you can follow to a framework, if you will, just to figure out how you would solve these types of questions, just generically for any type of version of that question. And we're going to go through an example of how you might do it. So when it comes to cubics, a lot of the time what you're dealing with is volume. That's because you have an x cubed term. So cube, of course, meaning like if you had centimeters cubed, that is a volume, versus squared being an area, or just centimeters being a length. You're in 3 dimensions cubed. But okay, we've got some information. Length of 20 centimeters, width of 10 centimeters, cutting out some x's on the side, and then forming a box. This shows up all the time. Excuse me, this shows up all the time forever. This time we're looking for maximum volume of the box. So if we're interested in the volume, we should first figure out what is the equation that describes volume. That's what this first step is. Create or find the equation that describes the quantity using only one variable. That last bit is important. We'll look at what that means. So volume of any box is going to be length by width by height. And so all I've done here is draw a little picture of what's going on. You would do this by hand, or at least I hope you would do this by hand. From there, what that means is instead of having this super long length of 20 centimeters, by cutting out these x's, you've now cut out an x from this side and from this side. And so you started with 20, your new length is now 2x less. Jeez, that was an unintentional tongue twister there. The same can be said for the width. So you started with 10, you cut 2 x's from either side, so you have 2x less. There, I said it right. Height of the box, this is something you'll need to know. The height of the box will always be the depth of the cutouts. So if you cut out x, your height will be x. If you struggle to visualize that, just try it in real life. Grab a sheet of paper, cut some x's out, fold it up, you'll see pretty quickly what I mean. It'll be a nice little arts and crafts for you. Okay, so from here, we know what our length is, what our width is, what our height is. This gets it purely in terms of x. So instead of saying volume equals length by width by height, we know length is 20 take 2x, so we put it there. Width, there. Height, there. That's all. I've done a bit of factorizing just to take some common factors out, but you don't really have to do that necessarily. I've just done it because I like doing it that way instead. Okay, that's our function. What we do here is draw a rough sketch of that function over its maximal domain. I say a rough sketch because you don't necessarily need to know every key feature about it, just enough to draw the overall shape. So, what does that look like? Well, we have a positive x, a negative x, a negative x. The net result of that will be a positive cubic. Negative times negative makes positive, and then times the positive again to remain positive. So we start bottom left, end top right. Then the solutions to null factor law give us the intercepts. So x equals 0 is there, x equals 10 is there, and then 5 minus x is going to give you x equals 5. And all you got to do is just loop around until you cut through those spots. Now, that's what the full cubic looks like. We want to know what the cubic looks like over its valid maximal domain. What does that mean? Well, remember that x, did I say it? No, I didn't say that just yet. Well, remember that x is a cutout. It's cutting from this box. And so there's a theoretical limit to how much you could cut out. For example, could you cut out 10 centimeters? Well, if you tried, you would have one x is cutting out 10, and then the other x on the other side would also try to cut out 10. Not going to happen. There's nothing left. And so the absolute max that you could have is x equals 5, because you'd have 5 on the left, 5 on the right. You would be left with no box, but that would be your breakpoint, effectively. And the way you understand that is you pick the smaller of the two lengths. Like, sure, you could cut all the way up till 10 from here, but because these all have to be x, you have to look at the smallest length to begin with, which would be the 10 centimeters here. So we cut it off at x equals 5. We should also cut it off at x equals 0 because, well, again, cutting out 0 is pretty much you can think of it as the bare minimum. We consider it undefined for the function. The point really being is that you don't want to have a negative x. Negative x, negative length, not going to happen. Not in the real world anyway. So that's what we cut it off here. The other thing I mentioned is that the height, the volume is on the y-axis. And so the other thing you might want to consider is that your volume cannot be negative either. And so everything below the x-axis should be eliminated. Although if you just look at the x, you should be fine. I haven't seen a situation where you need to also consider the y, but just be mindful that technically speaking, both have to be true. From here, it's nice and easy. Just observe what is the biggest value or smallest value on that graph, depending on what you're trying to solve for. In this case, we're looking for maximum. Well, there it is. That's the tallest spot. So we have to find that. Now, again, CAS, if this is non-calculus, and so you're just going to use, in this case, I've mentioned the Analyze Graph tool. So you go to Menu, Analyze Graph, and search for maximum. So if we were to do that with let's just do some random curve. Let's just say it's negative x squared. We'll even bump it up a little bit so we can be fine with it. Okay, menu 6 for Analyze Graph, and then 3 for maximum. You click, highlight, click, and it tells you the spot. Now, it could be way more complicated than that, but you still just click left, right, it tells you the spot. And on the Casio, you're going under Analysis, Gsolve, and Max. So let's try to do the same thing. Just keep in mind that I am a little bit less skilled on the Casio than I am on the TI Inspire, and so I will do my best to not suck. Okay, cool. Let's go back. Oh, already failing. Menu, please. There we go. Let's see. Graphs and table. And let's just cancel that whole thing away. Let's try to do the same thing as before. Negative x squared. Hopefully it figures this out. Yes, it did. Cool. Where's my graph? Can I just zoom in? Quick zoom. Oh, it's got to be something. Let's set that. No, wrong thing. That's what I get for trying to click things through a camera as opposed to... Damn, I did it again. Okay. Move the camera out the way for a second. Table. For this. Yeah, close enough. Okay. Box, zoom. Can I just drag? Really, I just can't do it, can I? It's got to be something. Maybe this. Oh yeah, that'll do actually. Negative 5 to 5. Dot can be whatever it wants. I'm not particularly fussed. That's probably a bit tiny. That'll do. Cool. Okay, we have our graph against all odds. Okay, now analysis, Gsolve, max. Analysis, Gsolve, max. There we go. 0, well, it's a bit tall. There we go, 0,2. As I said, worse at the Casio than I am with the TI Inspire. We'll pretend it's we'll pretend it's the Casio's fault and not my fault. I've mentioned here, tech-free, you would need to find the derivative of your function and set it equal to 0, which you wouldn't really be asked to do. But if you were to do your CAS-style tools, you would end up with an x value that is equal to this, as you see here. Why is that? Huh. It's a weird shape. Anyway, got distracted there. You would get x equals 5 minus root 300 on 6, which would be the x coordinate of this spot here, of the actual thing we're trying to solve. And so all you would do is sub that back into your volume equation to figure out the volume at that spot, which typically you would rewrite as a decimal, rounded to some number of decimal places. Usually you don't want to have, well, whatever this ends up looking like as a closed form answer. And that's it really. So we looked at how to do families of functions, which is just all these different possibilities for cubics, and then how you can solve maximums or minimums. Usually it's maximums though. Alright, till the next one.